Today we're going to talk about exponential and logistic modeling. To review from the other day, we discussed logistic modeling, and we discussed a function f of x which equals c over 1 plus a times b to the x. For this logistic model, c we called a carrying capacity or a maximum capacity. This is the top end. This is the upper bound of what our function can be evaluated at. In the denominator, we notice the a plus bx, which is very similar to our exponential function. The other function that we dealt with was an exponential function. Exponential functions are characterized by having a variable in the exponent location. We use g of x times equals a times b to the x power, where x is our variable. We're going to expand on this thought today, and we're going to create a new equation. P of t equals p sub 0, 1 plus r to the t. This is going to be very similar to the a times b to the x, except now we have p of 0 times a quantity that is our base to the t power. This is a good function that will model population. It will model amounts of money. And here are our variables. P of t is our population at some time, at time t. P sub 0 is our initial population, or initial amount of money, or initial quantity. R is our percentage increase or decrease, listed as a decimal. And finally, t is our time, and that needs to be coordinated with the percent increase or decrease. We're going to get into a couple examples here. The first example problem is a population that's initially 100,000 is growing at 8% per year. The first thing we want to determine is determine that population in 4 years. We're going to use the population as a function of time equals initial population 1 plus r to the t power. We're going to substitute in here. P of t is the population that we're looking for at 4 years. The initial population is 100,000. We're going to substitute in here. P of 4 is what we're looking for, the initial population of 100,000. 1 plus, as a decimal, 8%. And t here is going to be 4 years. This is something that we can solve algebraically. We do not need our calculator's graph or any graphing utility for this. We might need to use our calculator to do some computations, but we've got 1.08 to the 4th power times 100,000. P of 4 will yield a value of 136,048.896. Part B here throws away the 4 years. We're now going to talk about P of t equals the initial population 1 plus r to the t. We still have that initial population of 100,000. We still have that growing at 8%, but now we have a population and we're determining the time. So when we substitute in, we know the population is 120,000 with an initial population of 100,000, a rate of 8%, and we're solving for t. We can simplify the right side of this equation, but we cannot yet combine the 1.08 and the 100,000. To solve this algebraically, we would need the use of logarithms. We haven't quite gotten there yet, so we're going to solve this graphically. We're going to graph y1, which equals 120,000, and we're going to graph y2, which equals 100,000 times 1.08 to the t. This is going to be an exponential function. Those two are going to intersect exactly one time. We'll need our graphing utility to find the location of that intersection. Here's my image that I've created. F of x equals the 100,000 times the 1.08 to the t, or to the x. The g of x there is 120,000, and we're going to look for that intersection. It occurs at 2.369. Let's make sure we're always going to 3 decimal places, and we get a final solution here of 2.369. It's important to note units here. The units will be in years. In this equation, P of t equals P sub 0, 1 plus r to the t, there are 4 variables. Currently, we've solved for the population at a specific time. We've also solved for the time. Now we're going to solve for the initial population, and we're also going to solve for the rate. So we have 2 new questions here. Question 1. There's a bank account set up 10 years ago, currently worth $500,000. Determine the initial value if it is grown at 6%. So let's write out our formula. P of t equals P sub 0, 1 plus r to the t. P of t, that's what the account is worth now. So my account is worth $500,000. I'm looking for the initial value. So I'm going to leave P of 0 in there. I know the rate to be 6%, and I know the time to be 10 years. I'm now going to solve for P of 0. This is another equation that I can solve without a graph and without logarithms, but I might need my calculator to help me with the computation. 1.06 to the 10th power, I'll divide that into 500,000. I'll get P of 0 equals 279,197.39 cents. This is an instance when we're talking about money that I will allow you to round to 2 decimal places. The second problem we're going to do here is still going to use our population as a function of time equals P sub 0, 1 plus r to the t. The difference is we're going to determine the rate. We're going to determine the percentage growth if the initial value is 400,000. We know that the current value is 500,000. We know that the initial value is 400,000. We are looking for the rate, and we know the time to have occurred over 10 years. We could solve this algebraically by dividing the 400,000 over. And then to get rid of the 10th power, we would have to take the 10th root of 5/4. We're then going to subtract a 1 over, and r would be equal to the 10th root of 5/4, which I can compute in my calculator, minus 1, which is approximately 0.02257. I should interpret this to be a percentage of 2.257%. I've now used the P of t equation to solve for the population at some time, to solve for the initial population, to solve for the rate, or to solve for the time. Keep in mind, this population doesn't have to be a population. It could be a quantity of anything that is increasing at a set rate. I'm now going to ask you to practice some logistic modeling. I have here a problem where students in a high school start a rumor. The rumor spreads logistically, and the logistic function is given below. S of t equals 325 divided by 1 plus 24e to the negative 0.9t. T represents the amount of students that have heard the rumor at the end of that many days. I'd like you to first determine the number of students who have heard the rumor by the end of day 0. I'd also like you to determine the number of days until 250 students have heard the rumor. We might need our graphing utility for that. The second, and this is a real challenge, I'm asking you to write a logistic function that has an initial value of 10, a carrying capacity of 40, and contains the point 1, 20. I would keep in mind f of x needs to follow the form c, 1 plus a times b to the x. Graphically, we should have an image that looks like a logistic function with a carrying capacity of 40, an initial value of 10, and also contains the point 1, 20.